Let H be a Hilbert space and x0 be an element in that space. Then we can define a map or functional phi x0 from the Hilbert space to real numbers in terms of the inner product between x and x0 in the Hilbert space. Then we can show that this map or functional is linear and also bounded in some sense. Now, according to the Riesz Representation Theorem, the converse is also true. In other words, any functional that is linear and bounded, there exists a unique element in H, x0, such that the functional can be represented in terms of the inner product. Okay, let's start. So we have this map phi x0 of x, which is defined in terms of the inner product between x and x0 in the Hilbert space. In the following, for simplicity, we just omit this subscript h. So first thing we need to do is to show that this is a linear map. Okay, so x and y are any elements in H, and let's say alpha and beta are any real numbers. Then phi x0 of alpha x plus beta y is, according to the definition of this map here, we have alpha x plus beta y here times x0. So using the properties of inner product, this can be split as alpha inner product between x and x0 plus beta times inner product between y and x0. But this is just alpha, so this part is phi x0 of x, and this part is beta phi x0 of y. So the map phi x0 is linear. Next, we want to show that the map phi x0 is bounded. But what do we exactly mean by bounded? To define that, we first need the notion of magnitude of the map, which is norm of the map. So here it is, phi x0. Its norm is defined as the supremum of the value of the map phi x0 of x, where x is any element of the Hilbert space whose norm is less than or equal to 1. Okay, so we want to show that this is bounded. That means it's finite. By the way, we call this quantity a norm because it satisfies all the axioms of the norm. But we don't prove it here. So if you're interested, just try it. So, how we can prove this? First, note that the range of x is restricted in this range. So, if the norm of x is less than or equal to 1, we have the following. The absolute value of x0 phi or x0 of x is equal to, according to the definition, is the inner product. Okay. Now using the Cauchy-Schwarz inequality, we have the norm of x times the norm of x0. But here we have this condition. So this is less than or equal to the norm of x0 alone. So this implies the norm of phi x0 is less than or equal to the norm of x0. And next we consider two cases separately. First, if x0 is not 0 vector, then let x be x0 divided by the norm of x0. So normalize x, and then the norm of phi x0, since it's a supremum, right? So it's supremum of this. So this is greater than or equal to the value of phi x0 of this x. Okay. But using the definition, we have x0 times x0. So we have x0 here and x0, x0. But this is the norm squared, so x0, x0 squared, which is x0, norm here. So therefore, to summarize, the norm of phi x0 is greater than or equal to the norm of x0 here. So combining this and this, we have the norm of phi is equal to the norm of x0. So this was when x0 was non-zero, but what happens if x0 is actually a zero vector? Actually, when this is the case, then this is also true. So either case, this holds. And of course, x0 is some one specific vector in the Hilbert space. This is bounded. Therefore, the map is also bounded. Okay, now let's consider the converse. For that, let's define some terminology and consider a map phi from the Hilbert space to real numbers. And if this satisfies the following, we say it's a linear functional. Is a linear functional if and only if, by definition, for any x and y in the Hilbert space and any alpha and beta in real numbers, phi of alpha x plus beta y is equal to alpha phi x plus beta phi y. So in this case, we call it a linear functional. And we also define the norm of the functional, the linear functional of phi is this supremum of the value of phi of x, where x, the norm of x is less than or equal to 1. And we say phi is bounded if and only if the following holds. That is, the norm of phi is finite. Now, let phi h to real be a linear functional. And phi is bounded if and only if phi is continuous. Here, phi being continuous means the following. This means if we have a sequence of points in the Hilbert space that converges to some value, then the limit n going to infinity phi of xn converges to phi of x. So this means phi is continuous. So this theorem says being bounded and being continuous, they are equivalent. So let's prove it. Okay, first let's prove this direction. So suppose phi is bounded. Then for any x in the Hilbert space, and assume x is non-zero, then the absolute value of phi of x over x norm. So based on the definition of the norm of the functional, this should be less than or equal to the norm of the functional, because this is defined in terms of the supremum of the functional value. So anyway, but this is, phi is a linear functional, so this is equal to 1 over x norm times the absolute value of phi of x. So therefore we have the absolute value of phi of x is less than or equal to the norm of phi times the norm of x. Okay. By the way, this norm is the norm of the elements of Hilbert space, and this norm is the norm of the functional. So they are actually different norms. And now, if we have a sequence in the Hilbert space that converges and going to infinity xn, then 0 less than or equal to, we want to show that phi is continuous. So let's take the difference between phi of xn minus phi of x. But phi is a linear operator, so this is equal to phi of xn minus x. But using this inequality, this is less than or equal to the norm of phi times the norm of xn minus x. But since xn converges to x, this one converges to 0. So this converges to 0 as n goes to infinity. Therefore, phi of xn converges to phi of x as n goes to infinity. Therefore, phi is continuous. Next, we prove the converse, and we do by contradiction. So suppose phi is not bounded. What this means is the following. For any natural number n, there exists some xn, an element of the Hilbert space, such that the norm of xn is less than or equal to 1, and the absolute value of phi of xn is greater than n. Now, let's divide both sides of both of these expressions by n. Then we have xn over n, its norm is less than or equal to 1 over n. And the absolute value of phi of, since it's a linear functional, so we have xn over n greater than 1. Now, let's consider the limit of n going to infinity. As n goes to infinity, the absolute value of xn over n, the norm of this one, converges to 0. But this one still greater than 1. But since phi is a linear operator, phi of 0 is equal to 0. So that means phi is not continuous. But of course, phi should be continuous, so it's a contradiction. So the converse has been proved. Now, let us present the Riesz Representation Theorem, which says the following. Let phi h to r be bounded linear functional. Then there exists a unique element x0 in the Hilbert space such that phi of x is represented as the inner product between x and x0 for any element x in the Hilbert space. So any bounded linear functional is essentially an inner product. Okay, let's prove it. For the proof, first let us define M as the kernel of phi. This kernel is not the same kernel as the kernel functions, but it's a different meaning, which is the set of elements in the Hilbert space that maps to 0. Okay, and we show that the dimension of M complement, so this is the orthogonal complement of this M, is 1. Okay, first let Z be an element in M complement which is non-zero. So in particular, this means phi of Z is not equal to 0. And let Y be another element from M complement such that the inner product between Y and Z is equal to 0. So Y should be orthogonal to Z. And our goal here is to prove that this Y should be necessarily the 0 vector. Okay, then since phi of Z is non-zero, there exists some real number lambda such that lambda phi of Z is equal to phi of Y. And remember, the value of phi is a real number. So it's a real number times real number, which is equal to another real number. So this is always possible. And by rearranging this, we have phi of lambda Z minus phi of Y is equal to 0. But due to the linearity of phi, we have phi of lambda Z minus Y equal to 0. So this means lambda Z minus Y is an element of the subspace M. It's in the kernel of phi. Now let's calculate the norm of Y squared. And this is, of course, the inner product between Y and Y. But to this, we can also add, because of this, the inner product between lambda Z minus Y and Y. Because lambda Z minus Y is in M and Y is in M complement, they are orthogonal to each other. So this inner product is actually equal to 0. So that's why we can do this. And now let's combine these two products, and we have Y plus lambda Z minus Y times Y. And this Y and this Y will cancel, and we have lambda Z Y. But by the way we chose Y, this inner product is equal to 0. Therefore, the norm of Y is 0. That means Y is the 0 vector. So to summarize, any Y in M complement, if Y times Z, the inner product is equal to 0, that implies Y is equal to 0. Of course, don't forget that Z is in M complement. So, therefore, the dimension of M complement is 1. So, we can define M complement as this, lambda times Z, where lambda is any real number. Now, for convenience, let us redefine z by normalizing it. Okay, so this means now we have a unit vector z. Okay, so now for any element x in the Hilbert space, we can have orthogonal decomposition. So x can be decomposed into y and lambda z, where in this case this y is in M. Okay, and of course z is in M complement. Now let's calculate phi of x. So let's decompose x into y and lambda z. And because phi is linear, we have phi of y plus lambda phi of z. But y is in M, which is the kernel of phi, so this is 0. So it's lambda phi of z. And since z is a unit vector, so we can multiply by its norm. Okay, and we can distribute this constant here in the second position and lambda in the first position. So we have lambda z times phi of z times z inside. At this point, let's reintroduce y. Here, y times phi of z times z. This y is the same as this y, okay? But because this y is in M and this z is in M complement, this is just 0, okay? And then we repeat the previous line. And then combine these two products. And so y plus lambda z times phi of z times z. And y plus lambda z is x. So we have this. Now let x0 be phi of z times z. Then phi of x. So we started from phi of x here. So that ended up in the inner product between x and x0, where x0 was defined in this way. And we still need to prove the uniqueness of this x0. Okay, so for that, let y0 in Hilbert space be such that phi of x is equal to x times y0 for all x in H. So we have x0 equals to x y0. So that means we have x times x0 minus y0 equals to 0. And this holds for all x in H. So now this x can be anything. So let x be x0 minus y0. Then we have x0 minus y0 times x0 minus y0, which is equal to 0. It's equal to 0, right? But this one is equal to the norm of x0 minus y0 squared. Therefore, x0 minus y0 is equal to the 0 vector. Therefore, x0 is equal to y0. So this x0 is unique, and we are done. Next, let us define the notion of a reproducing kernel Hilbert space, or RKHS. Okay, let X be a set. This can be any set. And H is a Hilbert space consisting of functions from X to real numbers. Okay. And we assume H, this Hilbert space, satisfies the following condition. That is, for any X in X and any sequence of functions Fn and F in the Hilbert space, if limit of n going to infinity, Fn minus F, so this functional sequence converges to F, then the limit of Fn of X is equal to F of X. Okay, so if this condition is satisfied, then we say this Hilbert space is a reproducing kernel Hilbert space. Okay, here what this condition means is that the application of function f of n to x is continuous. Okay, so usually for defining continuous function, we consider a sequence of xn which converges to x, and f of n xn converges to f of x. Then we say f is continuous. But here it's opposite. It's not the sequence of x, but it's the sequence of f that is converging here. Okay, so the application of fn to x, that is continuous. This operation is continuous. And next, we show that this condition is actually equivalent to the following condition. That is, for any x in X and for any f in H, there exists some function kx in H such that f of x is equal to the inner product between f and kx in the Hilbert space. Okay, now let's show that this condition is equivalent to this condition. Okay, to do so, let us define a functional. So let us define functional phi of x from H, the Hilbert space H, to real numbers by this. For any f in the Hilbert space, so this maps to phi x of f, which is defined as f of x, which is a real number. Okay, if we define phi x in this way, then we can show that this is actually a linear functional. It's actually easy to see. So if we have phi x of alpha f plus beta g, say, and f and g are functions in H, and then we define this as alpha f of x plus beta g of x, which is alpha phi x of f plus beta phi x of g. So it's a linear functional. Now, using this notation, the first condition here, this one, can be translated as follows. So let's rewrite the first condition again. So if we have fn converges to f, then we have limit of fn of x equals to f of x. So using phi of x, this can be written as, so this one can be written as limit n going to infinity phi x of f n equals to phi x of f. So this means phi of x is continuous. It's a continuous functional. And previously, we have proved that this is equivalent to phi x is bounded. So that means phi x is bounded and linear. So we can apply the Riesz Representation Theorem. Therefore, there exists some function kx in H such that phi x of f is equals to the inner product between f and kx in H. So we are done. And what this means is that, so of course, this phi x of f is equal to f of x. So that means f of x is expressed as the inner product between f and kx in the Hilbert space. So functional application can be expressed as an inner product. And that is a characteristic of a reproducing kernel Hilbert space. Okay, that's all for this video. See you next time. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.